So good afternoon, everyone. Let us start today's 8 week discussion, 8 weeks discussion of lecture as well as solving. So this week basically, it will be a summary course of the last 7 week courses of the last 7 week classes which we have held, and we will be taking few case studies of various objects in order to understand the life cycle, how it is applied. Okay, and with that also we will the class also has a few tutorials. Okay, and apart from that we will be also problem solving a few more questions as we have done in the last 7 classes. Okay, so let us start today's discussion. So basically, if you see, remember this from the last class. So these are this is the flowchart of some performance indicators. Okay, so where you will find the midpoints and endpoints. So these are the midpoints, say global warming, ozone depletion, smog formation, acidification, ecological harm, and endpoint is basically human health and ecosystem damage. Okay, so this is a standard one. And if you talk about the CFC emissions, that is chlorofluorocarbon emission, so here if you see, the endpoint damage will be basically skin cancer, crop damage, immune system suppression, damage to materials, material life damage, marine life damage, and cataracts. And this will be because of the increased UVB radiation. So B is basically the ultraviolet radiation, which has a shorter wavelength and it causes basically sunburn. Okay, so it has a high intensity or energy. So this leads to the following damages. And if you see, I talk about the midpoint indicators, so there will be ozone loss in stratosphere, ozone depletion level potential, ODP, etc. Okay, so the if we talk about life cycle impact assessment, the emissions and waste from a product life cycle constitute the inventory upon which environmental impact indicators are based. Life cycle inventories do not by themselves characterize the environmental energy performance of a product, process, or service. This is because overall quantities of waste and emissions as well as raw material and energy requirements must be considered in conjunction with their potency of effect on the environment. Simply stated, a pound of lead emitted to this atmosphere has a different environmental impact from a pound of iron emitted to surface waters. Obviously, these two are different cases, so the impacts will also be different. To develop an overall characterization of the environmental performance of a product or process throughout its life cycle requires that life cycle inventory data be converted into estimates of environmental impact. Okay, the process of producing life cycle impact assessments is generally divided into three major steps. One is classification, one is characterization, and one is evaluation. So basically, classification is where inputs and outputs are determined during the inventory process, and they're classified into environmental impact categories. For example, methane, carbon dioxide, and chlorofluorocarbons, as they would be classified as global warming gases. Okay, and in case of characterization, it is where the potency of effect of the inputs and outputs on their environmental impact categories is determined. For example, the relative global warming potentials of methane, carbon dioxide, and CFCs would be identified in this step. And in valuation, where the relative importance of uh, each environmental impact category is assessed so that a single index for environmental performance can be calculated. So classification, if we classify basically, that is one of the important steps in life cycle impact assessment. So here inputs and outputs that were subjected of the inventory are classified into environmental impact categories such as global warming, stratospheric ozone depletion, photochemical smog formation, human carcinogenicity, atmospheric acidification, aquatic toxicity, terrestrial toxicity, habitat destruction, depletion of non-renewable resources, and eutrophication. So we basically have gone through all these impact categories in the previous classes. And as an example of classification, consider a list of air emissions inventoried for a study that compared glass and polyethylene given below. So carbon monoxide emissions are higher for polyethylene than for glass on a mass basis, while emissions of atmospheric oxides are higher than for glass than for polyethylene. The nitrogen oxide emissions would be classified as photochemical smog precursors, global warming gases, and acid precipitation and acid deposition precursors. And carbon monoxide emissions, on the other hand, would be classified as a smog precursor. So that is basically classification. Okay. So second comes characterization. So the second step of impact assessment, which is characterization. So it generally consists of assigning relative weights or potencies to different types of emissions, energy use, and materials use. These potencies reflect the degree to which the environmental elements contribute to environmental impacts. For example, if the impact category is global warming, then relative global warming potentials can be used to weight the relative impact of emissions of different global warming gases. Once these potency factors are established, the inventory values for inputs and outputs are combined with the potency factors to arrive at impact scores. Okay. So the general form of a dimensionless environmental risk index indicator is defined as, say, dimensional risk index I equal to EP into IIP I by EP IIP B, where EP is emission potential, IIP is particular impact indicator, and here the basically the subscript B stands for the benchmark compound, and I subscript stands for chemical of interest. To estimate the indicator capital I for a particular impact category due to all of the chemicals released from a product system, we must sum the contributions for each chemical weight by their emission rate. That is, capital I equal to summation I dimensionless risk index I into Mi, that is mass of the particular gas. So let us understand this in a better way, with taking some examples in the coming slides. So say this is a problem, example problem. So global warming index for air emissions of 111 trichloroethane from a production process. So here are some of the results. So 111 trichloroethane 11 TCA is used as an industrial solvent for metal cleaning as a reaction intermediate and for other important uses as per WHO in 2000. So sources for air emissions include distillation condenser vents, storage tanks, handling and transfer operations, fugitive sources, and secondary emissions from wastewater treatment. This example will estimate the global warming impact of the air emissions from this process, include direct impacts to the environment from 111 TCA and indirect impacts from energy usage, CO2 and N2O release in your analysis. The following data show the major chemicals that impact global warming when emitted from the process. Determine the global warming index for the process and the percentage contribution for each chemical. So this is the data provided from the air emissions air emission category. So for TCA, CO2 and N2O, TCA is basically trichloroethane. So here are the masses, okay. So 10 kg per hour, 7,760 kg per hour, 0.14 kg per hour, and GWPI is basically global warming potential. So for each chemical, it has been assigned a value in terms of CO2. Okay? So this is 100 CO2, this is 1 CO2. CO2 is basically one only, it will be one equivalent only, and N2 is 298 CO2. Okay? So 101 and 298. So this is the source from where it has been taken. So we need to find the global warming index for the process, okay, and the percentage contribution for each chemical, okay. So the global warming index is basically, it will be IGW. So this will be summation of the products of all the three, okay. So that is equal to 10 into 100 plus 7 into 7,000, sorry, 7,760 into 1 plus 0.14 into 298. So if you multiply and add, so we will get 8,801.7 kg per hour. So that is the global warming index, and the percent of the process IGW for each chemical. So that is basically in numerator you have to find the you have to give the product, and in the denominator you have to give the global warming index. Okay, so it is for 111 TC, it will be 1000 by 8801.7 into 100. 100 is multiplying for percentage, so it is 11.4%. For CO2 it will be similarly this 7760 by 8801.7 into 100 is 88.1%, and for N2O it is basically 41.7 by 8801.7 into 100, that is 0.5%. Okay, and this is the basically formula for global warming index. Okay, so similarly, let us take one more example for further understanding. So comparing electricity generation by fuel type, electricity is one of the most important forms of energy that is used in industry, commerce, and private residences. In this example, a list of pollutant emissions to air will be listed for different electricity fuel types. The emissions will be classified into different impact categories and their impact potentials characterized. Finally, environmental indicators will be calculated from the emission and impact potential data. So, emissions of gaseous pollutants based on the production of 1 kilowatt hour of each electricity type are shown in the table below. So, it is given in the next slide. So this inventory data represent a compilation over the entire life cycle from extraction of raw materials from nature to the output of electricity from the power plant, a cradle to get inventory. Okay. So you see, this is the table provided as per the data. Okay. So from here, if we want to say, for example, if we uh, so this is the data provided. So yeah, so we'll be basically finding the global warming index. Okay, so IGW initially, so that is equal to summation I GWPI into MI, right? So in the case of so for every chemical and its sources basically, so if you want to find the global warming potential, so just multiply this GWP into the mass. Okay, so mass is this mass. Okay, so for example, in the case of hard coal, this is 29.01 into 298. Okay, so it has been shown also. So it is 29.01 into 298. So that you will get in milligram, but here it is gram. So you will divide by 1000. Okay, so it is 8.64 gram. Okay. Similarly, this value for this oil for dinitrogen monoxide in oil, so you'll multiply 43.06 into 298 divided by 1000 for converting to grams. So it is 12.83. So similarly, you can find out every value. Okay, for methane you have to take GWP as 25 and for carbon dioxide as 1. And based on this, you can just add. Okay, so for hard coal, for all the chemicals, if you add, you will get the global warming index as 1189.49 gram. So similarly, for oil, it is 884.86. For natural gas, it is 683.87. For nuclear, 12.00. For hydro, it is 5.10. For wind, it is 11.28 gram. For PV, that is photovoltaic. Okay, so it is 44.34 gram. Okay. Now, similarly, if you want to find the acidification index (IAR), it is equal to summation of ARPI into MI. Okay, so ARPI is basically acidification. Okay, so acidification. Sorry, it is ARPI is acid rain potential. Okay, ARPI is acid rain potential. So this potential for nitrogen oxide is 1.07. For sulfur dioxide is 1.0. So other than that, others have been considered say 0. Okay, it is not provided, so we'll only consider these two. So if you multiply similarly, if you for say for example in the nitrogen oxide for hard coal, so you can just multiply 2.55 okay into 1.05, so you'll get 2.72. Okay, similarly if you want oil, sulfur dioxide in oil, so it will be basically this one, yeah, 6.60 into 1. Okay, so that is 6.60. So similarly you can find all the values and adding you get the acidification index IAR. So that is for hard coal 7.99 gram, for oil it is 9.54 gram, natural gas 6.19 gram, nuclear 0.10 gram, hydro 0.02 gram, wind 0.06 gram, and photovoltaic it is 0.26 gram. Okay. Similarly, for smoke formation index ISFP, ISF, it is equal to summation of SFPI and into MI. So this is SFP is basically smoke formation potential, and MI is the masses, are the masses. Okay. So here we have considered two chemicals. One is NMVOC, that is non-methane volatile organic compounds, having an SFP value of 3.10, and methane, which is having a SFP value of 0.015. So for example, for the hard coal case, you will get the value as this one, 29.01, and sorry, it is 126.14 into 3.10 divided by 1000. Okay, because we have converted into gram, so it is 0.39. Okay, it's 39 grams. Similarly for oil, it will be oil from methane, it will be this one, 0.48 into 1.0, sorry, 0.015, 0.48 into 0.015, and both are in grams only, so it will be you don't have to divide by 1000, so it will be 0.01. So similarly you can put the values for all the categories, and finally summation by adding you will get the smoke formation index. So it is for hard coal 0.41 gram, for oil 0.85 gram, for natural gas 0.62 gram, nuclear 0.02 gram, hydro 0.01 gram, wind 0.02 gram, and photovoltaic it is 0.16 gram. Okay. So this comparison shows that electricity generated from coal and oil has the highest impact on the environment and that renewable power from hydro, wind, and solar, that is photovoltaic, are among the best alternatives based on these indicators. Nuclear also exhibits very low impacts for these indicators, but the same conclusion may not apply if human health indicators and other types of impacts are included. These results can be used to inform decisions about investments in future power production and also in consumer decision making on whether or not to purchase green power. Okay, so if you talk about human and ecosystem health, okay, so environmental indicators such as GWP, that is global warming potential, ODP, that is ozone depletion potential, ARP, that is acid rain potential, and SFP, smoke formation potential, are based on cause and effect mechanisms involving physical and chemical transformation of pollutants. And the indicators for human and ecosystem health rely on both objective as well as subjective factors. Okay, so in case of objective, it is both physical and chemical. Okay, so the Tracy method is one of the more objective science-based indicator sets for human and ecosystem health. It is based on a multimedia FATE, multi-pathway human exposure and toxicological potency approach. 23 exposure pathways were taken into account, including inhalation, ingestion of water and food, and dermal contact with the soil and water. Toxicity is based on cancer potencies for carcinogens and reference the doses or concentrations for non-carcinogens. So this is some data based on rankings of 1993 releases of chlorinated organic compounds in the Great Lakes Basin for several potency factor schemes. Okay, so for various toxicity as per various organizations, the rankings have been given for various compounds, as you can see. So similarly, let us talk about the social performance indicators. So engineers often incorporate social concerns in the design of products, infrastructure and systems by considering the end user functions and interactions. But social impacts within the context of sustainability move well beyond end user functions to the fulfillment of human needs and improvement of the human condition. These needs and social conditions span a range of issues from fulfillment of basic nutritional, sanitation, and security requirements to higher level human aspirations in areas of health, education, and the arts. But how can engineers incorporate elements of social sustainability into design in a formal fashion? So that is a question. Okay. So if you see here, it is a table showing selected UNDSD, that is United Nations Division for Sustainable Development. So UNDSD indicators for social sustainable development. Okay. So these are the themes, these are the sub themes, and these are the core indicators. So this is how we will be able to find the various parameters and various characteristics based on the various indicators. Okay. So if you similarly, if you see here, it is a social sustainability stakeholder category, okay, and indicators within each category. So these are the categories. One is employee working condition. One is international community. One is future generations. One is consumer. One is local and national community. And within this, you have various indicators. Okay, so this is how we need to analyze. So, in summary, if we say, we talk, engineers play an important role in global sustainable development by developing and commercializing uh, technologies that allow for a high standard of living with favorable economic returns, minimum environmental impact, and with regard to the social conditions of stakeholders. This lecture provided engineering design principles to address environmental issues and introduce an environmental perspective on engineering economics, presented an overview of environmental indicators, and outlined a framework for social sustainability assessment. Taken together, these approaches, methods, and frameworks are valuable addition to an engineer's design toolbox. Okay, so these approaches, methods, and frameworks are valuable for an engineer's design toolbox. Okay, so that is why it is important to find this understand these various indicators and categories. Okay, so if we talk about a, say for example, take a particular example. Okay, so technological and life cycle assessment of composting and AD, that is anaerobic digestion odor control technologies. So if we talk about this composting and anaerobic digestion odor control technologies, and based on this we will perform LCA. Let us see how we will proceed. Okay, so Here we will be having two phases. One is up till from introduction to key findings of assessment, and second is from goal and scope to conclusion and recommendation. So this is the basically the overview of this case. Okay. So introduction. So municipal solid waste management is an essential service which includes disposal, recycling, and organics processing. For a typical municipality in Canada, so we are basically talking about Canada case in Canada. Okay. So for a typical municipality in Canada, organic waste makes up to 40% of the municipal residential waste stream as per literature. More and more municipalities are implementing options for processing organic waste, which include both composting and anaerobic digestion. So although there have been great technological improvements, odor from composting and anaerobic digestion facilities continues to be a major issue. Okay, complaints often bring legal problems and in some cases closure of the facilities. Uh, for organic waste management, odor control is one of the most expensive and environmentally impactful components. Therefore, a good understanding of the different technologies available for odor control is very much crucial. Okay. So, why is odor still a problem? So, odors result from many different compounds interacting together in complex ways. Some of the common odor sources include hydrogen sulfide, organic sulfur, organic sulfides, ammonia, amines, okay, fatty acids, aromatics, methyl ethyl ketone, terpenes, etc. So the if you see here, basically the objective and scope of the project, the aim of the project was basically twofold. So there was two phases. One phase was identification and technological assessment of odor control technologies for MSW, that is municipal solid waste organics processing. And the phase two, in the phase two, it was basically life cycle assessment of select odor control technologies based on phase one results. So if you see the odor control technologies or methods, so there are various methods such as biofilters, activated carbon absorption, packed bed wet scrubbers, fine mist wet scrubbers, thermal oxidization, oxidization chemicals, masking agents. So these are some of the uh, available odor control technologies and methods in the market. So, firstly, if we talk about the biofilters, so they use microorganisms to degrade and destroy odor compounds, and this is a sketch of the basically a biofilter. So here, this is the foul air. It is coming inside from here, from down. This is a stream injector, and there is heat exchange happening. So from that, the basically it has a drain. Okay, and for like for excess air coming, so it will be like for any liquid, basically it will be injected with stream, so the liquid will fall down. Okay, and the gas basically it will enter. So perforated support plate is here, and bulk media filter bed is here. So it will go through the water sprinkler to motion filter, and finally the exhaust air, which is a filtered one without any odor. So like this it is controlled. Okay. So similarly, if we talk about activated carbon, so these are odorous compounds which have very high porosity, porous carbon materials, and so activated carbon are basically high porous carbon materials. So their odorous compounds are removed by absorption on activated carbon. Okay, so if you see here, gases and chemicals they are entering. Okay, this is the activated carbon, and they have a large amount of pores. So in these pores, they have very high surface area as close to 1400 meter square per gram of material. Okay, as per literature. So they are able to absorb the odor. Okay. Similarly, peg bed fine mist wet scrubbers. This is a sketch of that. So washes odorous. This washes they wash odorous compounds from airstream. Okay, into liquid scrubbing solution. Okay, so they remove the odor from airstream into liquid scrubbing solution through liquid scrubbing solution. So similarly, thermal oxidizers they destroy odorous compounds in the air by heating it to a high temperature. Okay, so between 1300 to 1600 degree Fahrenheit, EPA as per EPA 2000. And in chemical oxidization, chemicals react with odor causing compounds to form odor free compounds such as potassium permanganate KMnO4. And in masking agents, chemical agents used to mask odor compounds using patented compounds, essential oils, etc. So, if we go to technological assessment, so following factors are assessed. One is capital and O&M cost. O&M is basically operation and maintenance. One is volume of airflow handled. One is odor units removal efficiency. One is reliability, one parameter is space requirement, other is chemical and media usage, energy usage, and water usage. So these are some of the this chart represents some of the all the technologies and the order units removal, capital cost, okay, O&M cost, reliability, space requirements, energy usage, chemical media usage, water usage, and these are the references from where it has been taken. Okay. So from that, if we talk about the key findings of assessment, so from a technological efficiency, usability, and cost perspective, biofilters are preferred option. Pack bed which scrubbers also function well in composting and AD anaerobic digestion facilities, especially for more concentrated air streams. Fine mist waste scrubbers are not a preferred choice due to higher capital and operating costs. Carbon adsorption can be useful, but its applicability is limited to other streams where ammonia is not produced. Thermal oxidizers are not practical due to high cost, use of fossil fuels, and potential production of SOx and NOx. Oxidizing agents and masking agents can be used as part of odor management plan, but not effective as individual methods. So these are some of the key findings, okay, from the assessment. So if you talk about the LCA technologies, so looking at organics processing facilities across Ontario, that is our place in Canada. So it is found that biofilters are only odor control system used. So basically, people go for biofilter, and in Ontario, and in Guelph and Peel, they use a synthetic media, while in Hamilton and London. So London, this is not London from UK; it is from Canada. Okay, Guelph and Peel are also some municipalities in Canada, and Hamilton is also from Canada. Okay, so all places are in Canada. Okay, so in Guelph and Peel, they use a synthetic media, whereas in Hamilton and London they use organic wood chips media. Okay, so both systems have odor removal efficiency of 90%, which is similar to pack bed wet scrubber system. Okay, so this has been found as per some a particular literature. So thus, based on results of assessment and looking at industry practices, let us consider three technologies chosen for performing the life cycle analysis. One is synthetic media biofilter, one is wood chip media biofilter, and one is pack bed wet scrubber system. So let us talk about all these three technologies and talk from the and study from the point of LCA. So goal and so till here was the first phase. Okay. So now let us go to the second phase of the study. So the goal and scope of LCA. So LCA takes into account materials of construction from extraction, includes transportation, energy usage, water and chemical usage, and landfilling and recycling during decommissioning phase. SEMA Pro 8 software with its EcoInvent database processes were used, and all three technologies were assessed over 15-year period, since that is expected life of synthetic inorganic media. Okay, so that has been you can go to this literature for further for more information basically. So system boundaries and functional unit. So if you talk about this, these are the first part, and these are the important steps in life cycle analysis. So the geographical boundary of analysis is considered to be region of Ontario. Okay, so a big region they have considered. Facility in Guelph processes 30,000 tons per year of organic waste. Facility in Hamilton processes 70,000 tons per year of organic waste. All material, chemical, water, and energy usage for all systems scale to 1,000 tons per year. Okay, and boundary for each system only includes odor removal system and does not consider pre-treatment or pre-scrubbing of air. Since all three systems have a comparable odor removal efficiency, effect of treated air is not considered in the study. Okay. So now we will go to the data collection stage. So data for biofilters collected from facility in Guelph, which uses synthetic media, and facility in Hamilton, which uses wood chip media. Data for the packed bed wet scrubber system was collected from literature and previous studies and downscaled to 1000 tons per year. Okay, so that is basically the functional unit which we have considered. Okay. So the assumptions and limitations in this study were only materials, chemicals, and equipment with significant quantities were included in study. Small components such as screws, bolts, wiring, and etc. were considered to have a negligible effect. In terms of scaling data, it was assumed economies of scale have a negligible effect. It was assumed treated air based on 1000 tons per year would have negligible environmental effects which compared when compared to the effect of materials, energy, water, and chemicals usage. Reasonable assumptions based on common knowledge were made in the case of missing data. The databases made use of European world values. Okay. So the key data in inventory. So biofilter systems are divided into 5 sub-assemblies. one building frame, two biofilter media, three fan suction system, four water sprinkler system, and fifth is control and monitoring system. Whereas pack bed weight scrubber system that was divided into five sub assemblies: outer shell, packing materials, spray solution system, fan suction system, and control and monitoring system. So the biofilter well facility comprised of three concrete cells, three suction fans with 810 meter cubes of synthetic media, that is silica and alumina coated with mixture of ferrite, organic carbon, alkaline buffer, and hydrophobic chemical. Biofilter at Hamilton facility comprised of one big concrete cell, four fans, and 1200 meter cube of wood chips, which are changed every 2 years, and packed bed system comprised of fiberglass interlocks saddle packing material and uses sodium hypochlorite and sodium hydroxide as scrubbing chemicals. Okay, so so let us go to the impact categories which were assessed. So these were the 12 impact categories assessed. So for this LCA study, 12 impact categories were assessed, which were cumulative energy demand (CED), climate change, human toxicity, photochemical oxidant formation, metal depletion, fossil depletion, terrestrial acidification, freshwater eutrophication, marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, and marine ecotoxicity. So these are the impact categories considered for the assessment. So initially, the characterization and normalization was done. So characterization was basically scales the results by percentage based on the highest impact, and in normalization, it was done by dividing the impact category by the reference. A reference value can be found by looking at the average environmental load in a country or region over a year and dividing by the number of people. So this is how characterization and normalization was done. So the impacts of concern were based on the figures. One was metal depletion, one was fossil depletion, one was human toxicity, one was freshwater eutrophication, and one was marine ecotoxicity. So the key impacts, if we talk about the climate change. So although climate change impact was low, it is considered since it is always of concern. Fan suction system is responsible for most of the climate change effects for all three odor control systems. Electricity demand for the fan suction system was responsible for more than 80% of the climate change effects for each system. Okay. If we talk about metal and fossil depletion, it was found that fan suction system is major contributor to fossil fuel depletion for all three systems, particularly 24 by 7 electricity usage. Metal depletion impact of wood chip and pack bed system was fairly low, while the synthetic biofilter system had a fairly high impact. And more than 90% of this impact was associated with ferrite used to manufacture the synthetic media. Okay. So, if we talk about freshwater eutrophication and marine ecotoxicity, it was found that inorganic and wood chip biofilter systems had a fairly high freshwater eutrophication and marine ecotoxicity impact. The major contributor for both systems was the 24 by 7 electricity usage associated with the fan suction system. So if we talk about human toxicity, the packed bed wet scrubber system, there was 1278 kg of 14 dB, that is dichlorobenzene equivalent impact, and the fan suction system contributed 49%, the chemical spray system contributed 30%, and the SCADA, that is basically supervisory control and data acquisition control system, it contributed 18% of this impact. The wood chip biofilter system had a 2875 kg 14 dB equivalent impact. The major contributors are fan suction system, building frame, and wood chip media, which contributed 65%, 16%, and 11.5% respectively. Inorganic biofilter system had largest impact at 3513 kg 14 dB equivalent impact. Major contributors are fan suction system, inorganic media, and building frame, which contributed 55%, 30%, and 8% respectively. So, based on this, the discussion of the results could be as such as follows. For all impact categories, the inorganic media biofilter had highest impact, followed by wood chip biofilter system. The backbed system had smallest impact for all categories. The synthetic media showed higher impact level than wood chip media, even though synthetic media had lifespan of 15 years. This was and wood chip had to be replaced every 2 years. So although wood chip was replaced every 2 years, so it had a lesser impact level as compared to synthetic media, which had a lifespan of 15 years, almost 7.5 times more. Okay, so that was because wood chips are expected to be composted at end of life, while synthetic material was landfill. And secondly, synthetic material had a material intensive manufacturing process, which was not the case with wood chip media. Okay, the major contributing factor for all compact in categories was higher electricity usage associated with using a bigger fan suction system for the biofilters as compared to smaller system used for packed bed system. Biofilter systems had to draw odorous air through large surface area of material as compared to packed bed wet system, which used a single industrial fan. Inorganic media in biofilter was primary cause of high metal depletion impact. The synthetic media was coated with a ferrite solution. So based on this, the conclusion and recommendations part is as follows. Choosing system based on operational parameters, the biofilter systems were the recommended choice. Looking at O&M, that is operations and maintenance and ease of operation, the inorganic system is the preferred choice over wood chip system because media does not have to be changed often. And in terms of system with lowest environmental impact, the clear choice is packed bed system based on LCA. Thus, choice of system depended on what criteria is of importance. Is it cost, is it environmental impact, or is it system operation? So, if we talk about this, if we ranked the three systems based on cost, system operation, and environmental impact, we'll see that in terms of cost, the biofilter organic is the first. Okay, the biofilter inorganic is second best, and packed bed with scrubber is third best. If we talk about system operation, the biofilter inorganic was the best, the biofilter organic was second best, and packed bed with scrubber was third best. And if we talk about environmental impact, it would be seen that packed bed with scrubber was for best, biofilter organic second best, and biofilter inorganic the third best. So, for future studies, a more detailed cost assessment is recommended to get a complete picture. It may also be good to look at methods of making biofilter systems less energy intensive, since a sizable portion of environmental impacts is associated with fan suction system electricity usage. So, so that was all about the filter systems. Okay. So now let us take one more case. That is, let us perform LCA between kerosene lamp and solar lamp. Okay. So let us find out how the LCA is providing the how it is providing the results. So the goal is to compare a kerosene lamp to a solar powered lamp to determine a favorable solution. So the function is basically to provide adequate lighting for reading and writing, and the functional unit is greater than 100 lumens, 4 hours every day for 10 years. So for 10 years, 4 hours every day, it should have greater than 100 lumens intensity. Okay, so that is the functional unit. And the scope is so the database, it has been the values have been taken from SIMA Pro 7 database, and the scope is from raw material acquisition to material processing to manufacture and assembly and to use and service. Okay, so retirement and recovery and treatment disposal are not taken because the software does not have the data for this inventory for this. So it will be basically from it will be basically from cradle to gate. Okay, so it is not to grave because we don't have data for two categories, two systems. Okay, so if we talk about this one, uh, if we talk about the solar powered lamp, basically solar powered lamp, so it is Shenzhen Power PS L045. So Shenzhen is a place in China, so they manufacture this. So for this, the ingredients required are polyethylene, nickel metal hydride battery, printed circuit board, steel, polypropylene LED, that is light emitting diode, and solar panel. So these are ingredients for making this electric solar power, sorry, solar powered lamp. And these are the ingredients for the Shenzhen Power PS L045. Okay. So the assumptions are usable life is 10 years, assembled in Shenzhen, China, distributed in Tanzania, Africa. Okay. So for this, the requirements to get the raw materials. So for polypropylene, the polypropylene is transported. It is procured from Tokyo, Japan, by Mitsui and Corporation Limited. And for Polyethylene, they basically it is taken from Jinan, Shandong, China, and it is provided by Yongtuo Chemicals Corporation Limited. So they basically undergo polymerization. That is the ethylene propylene. They basically undergo polymerization reactions, and using like these are some hexanes, and so they react with hexanes, and for using some co-catalysts, they basically form these compounds. Okay. So the printed circuit board PCB, it is procured from Zhuhai, Guangdong, China. So it is provided by Zhuhai Westbright Technology Limited. The photovoltaic cell, that is PVC, so PV, so PV cell, that is procured from Linhai Taizhou, Zhejiang, China, and it is provided by Kingdom Solar Energy Technique Company. The light emitting diode, that is LED, so it is provided by Lightning Optoelectronic Technology SZ Corporation from Shenzhen itself, Guangdong, China. So that is provided by Shenzhen Easter Battery Corporation Limited, that provides the NIMH, that is nickel metal hydride battery. So if you see, this is the location where it is manufactured, and the raw materials are coming from far away as well as near places. So as close as 50 kilometer to as high as distant as 3,834 kilometer. So from that is the difference in distances from where the raw materials are coming to the place of Shenzhen for the creation of the solar lamp, solar bulb. Okay. So, if you see the processing, it requires metalworking, machine operation, steel, injection molding, polyethylene and polypropylene, propylene. So, assembly and packaging, it requires cardboard and polystyrene. Okay, so these are the requirements. And based on the LCA assessment done, life cycle assessment done using the SIMAPRO software. So these are the results. Okay. So the major impact categories are shown. That is climate change, human toxicity, ionizing radiation, agricultural land occupation, metal depletion, and fossil depletion. As well as minor impact categories are also provided, which are ozone depletion, photochemical oxidant formation, particulate matter formation, terrestrial acidification, freshwater eutrophication, marine eutrophication, terrestrial ecotoxicity, freshwater ecotoxicity, marine ecotoxicity, urban land occupation, natural land transformation, and water depletion. So these are being shown for all the sources of raw materials. Okay. So the assumptions are, firstly, tin, 2 year usable life, 1 mm thick, recycled in Nairobi, Kenya, and the other is, that is basically for, I think, the solar lamp, and for the normal bulb. Okay, so that is cotton, 2 year usable life, 3 by 4 inches wick diameter, processed, and that also in Nairobi, Kenya. Okay. So if you talk about this, so there is a kerosene basically. So the normal was the kerosene, and the other was the LED. Sorry, solar lamp. So for kerosene, say we use 10 gram woven cotton wick, okay, and 655 gram tin container, 5.5 liter capacity. So it requires kerosene fuel, which is C12H26. Okay, so that is an alkane basically. CnH2n plus 2, right? Where N is equal to 12. So if we talk here, if you see here the transportation, so for tin, the components, okay, so it requires 0.665 kg, distance kilometer is 352 kilometer, trips 5, ton into kilometer is 1.1528 ton kilometer. Cotton wick, it is 0.010 kg, 352 kilometer, 5 trips, and 0.0176 ton kilometer. So the land transportation total required will be 1.1704 ton kilometer. And for the kerosene lamp, these are the impact categories as shown. So, this is how the assessment is done. Okay. So let us take one more example. So let us perform life cycle analysis between bottles. Okay, so water bottles are made from using two materials. One is polyethylene terephthalate, that is PET, and other is polylactic acid, that is PLA. Okay, so both of them are used for making the water bottles, drinking water bottles. So let us perform a life cycle assessment and understand which performs better. Okay. So the bottled water market segment in the USA and Canada represents a $16 billion product category, typically made from polyethylene terephthalate, PET, non-renewable resource, and polylactic acid, which is a commercial interest in recent years in light of its renewability and compostability. So the bottled water industry is dominated by various companies such as Nestle, Pepsi, and Coca-Cola or Coke. So the first generation LCA of PLA, that is polylactic acid, was same fossil energy requirements. The current LCA, the fossil requirements 10 times lower due to energy utilization in production plant for the LCA. Few studies show no clear win but trade-offs. Calculations of impact depends on the system boundary. So these are some of the this one, uh, some of the uh, some of the findings that have been found based on the life cycle analysis, based on the processes and unit processes and the system boundaries they have been considered. Okay, so the goal and scope is basically for this LCA. The goal and scope is to compare the environmental impacts of PLA and PET drinking water bottles, this will be cradle to grave LCA because the data is available from right from the birth to the date. Okay, so that is from extraction of raw material up to the end of life. Okay, and the extraction of raw materials, procession, the process of resin production, bottle production, end of life disposal. So these are some of the processes. Okay, so the functional unit will be basically function of one bottle is provide 500 ml of water. 1000 units of 500 ml bottle to be used for drinking water. That is a functional unit. Okay. So bottles were considered to be of same mass and lifetime. So one bottle was about 12.2 gram. Okay. So 1000 bottles would be 12,200 gram or 12.2 kg. Okay. That is basically one piece. So one piece considered 1000 bottles, which has a weight of 12.2 kg. So these are the system boundaries and these are the processes basically. So the basically for PET granules there is extraction and refining of crude oil, and for PLA granules there is corn farming and wet milling. Okay, so these are done. So these are the raw materials, extraction of raw materials. So from transportation we get the next process, which is bottle production process. Then comes the bottles to consumer and then transportation to waste scenario. And during bottle production process there is process waste. Okay, and it requires CO2 resources. It requires CO2 resources. CO2 is for plantation. Resources is required during transportation. Water is required during processing. And the emissions. So these are inputs and outputs are emissions to air and water and waste basically. Okay. So this is the system boundary, and TR is basically transport. And the consumptions there is same for both the bottles, and so that can be excluded. So consumption is same for both the bottles because both will be solving the purpose of carrying 500 milliliter or say a particular volume of water. So it will be same for both the bottles, so we can exclude it because it will be nullified. Okay, both will cancel each other. So the methodology, so for that they people like it is the software, the people have used the software of Sima Pro. Okay, and it is Sima Pro TM pre-consultants Netherlands, and the database is EcoInvent database of USEI, that is US EcoInvent. And the processes are production of PLA and PET pellets granules, production of bottle injection and blow molding processes. So this is the blow molding process, and here this is the pre-preg. So that is pre-impregnated reinforcement fibers inside the resins. Okay, so that is pre-preg. So transportation, resin production unit to bottle production unit 1000 kilometer by truck, 1000 kilometer by train. Waste collection plant disposal scenario is 100 kilometer by truck. Okay, so for production of resin 1000 it has to travel by truck and 1000 kilometer by train. And for waste collection plant disposal scenario, the truck has to travel 100 kilometers. So the waste scenarios which have been considered are 100% landfill, 100% incineration, 100% recycling, 50% landfill as well as 50% incineration, 50% recycling, 30% landfill, 20% incineration. So five cases have been considered both for PLA and PET. The impact assessment, for performing that, two basically softwares were used. One was two methodologies were used. One was impact 2002 plus, considering endpoints, and one was recipe midpoint H. Okay, the assumptions were no bottle is being retained by the consumer, all undergo waste treatments. PLA and PET do not degrade in landfill due to anaerobic environment. Production efficiency of PLA and PET from recycled waste was 90%. All the recycled PLA and PET granules used for production of new bottles, and PLA was treated as PET. Okay. So normalizing all the scenarios, so based on the impact assessment methods, so these were the results for midpoint and endpoints based on the waste scenarios. Okay, so as you can see, taking all various categories of endpoint and midpoint into account. Okay, so similarly, if you see the toxicity, okay, in midpoint, taking the midpoint, that is the midpoint impact assessment. So if you see here, so it was found that toxicity decreased in the case of the PET, okay, polyethylene terephthalate bottles. So the toxicity decreased, but this decrease was, the question was, was it a significant decrease? Okay, was the decrease significant? So if you see here, the decrease was very less. Okay, so it is not that significant. However, if you saw the chart on carcinogens, okay, so it was seen that there was 750% reduction, 750% reduction uh, in the carcinogen emission in the case of PLA, okay, that is polylactic acid bottles, as compared to PET bottles, polyethylene terephthalate, because there was no need for purification of terephthalic acid. Okay, so the terephthalic acid purification basically resulted in carcinogenic release of carcinogenic substances. So without using PET or using PLA, there was a 750% reduction of carcinogen substances. Okay? So that was also seen here. So see in terms of if you see process contribution in terms of Kg C2H3Cl, that is vinyl chloride. Okay, vinyl chloride equivalent. If you see, so if you see here, in case of PLA, the purified terephthalic acid was very high as compared to 100% recycling PET, where it was very less. So that's why there was 750% reduction in carcinogens. Okay, so now the question is, which is better, PLA or PET? So PET, it is resulting in 750% high in carcinogenic substances in terms of KgC2H3Cl, that is vinyl chloride, and 22% high in non-renewable energy in terms of megajoule primary. In PLA, so it is resulting in 360% high land use in meter square, 5% high toxicity. So this difference was 5%. Okay, so that is not that much. So 5% high toxicity in terms of Kg 14 dB dichlorobenzene equivalent, and 13% high in climate change in terms of Kg CO2 equivalent. Okay, so so basically the assessment. So if you see, so from one impact category, one is better; from other impact category, the other is better. Okay, so that is depending on what impact category you are. We are considering. Okay, what categories we are considering, and uh, is it the endpoint or is it midpoint? Okay, so that is, so the midpoint is basically given by the recipe method, and the endpoint is basically provided by the impact 2002 plus in this example. So if you see here in the polylactic acid case, so if you see here, so basically they have here provided a single score value. Okay, so single score value has been provided based on the main categories. Okay, main impact categories. And if you see here, it is found that if you compare both, okay, so one is better in some particular impact category, whereas the other is better in some other particular impact category. But if you finally solve them into a single score, okay, and based on all the dumping methods, okay, all the end of life methods, so it can be it can be seen that the PLA is performing much better. Okay, so the PLA is performing much better. So if you compare the PLA here and the PET here, so it is less. If you compare the PLA here and the PET here, it is again less. If you compare this and this, again less. If you compare here and here, again less. If you compare this and this, again less. So it's PLA. Okay, so which is better? Polylactic acid is better. Okay, so this is how the finally the life cycle assessment result should be. It should be a single score value, so that it is easy for everyone to understand the finding. Okay, so the limitations and conclusions for this is, PET, it is basically a mature technology. So that is the advantage of PET. Okay, it is a very mature technology, whereas in case of PLA, it is an early stage of development. And also one problem with the industry is, like, industries are very reluctant to change. Okay, they want a very stable a stable process of manufacturing, okay, assembly line, so that they have a better idea of what is happening, okay. So that helps in efficiency also, and also helps in production as well as your commerce, okay. Commercial factor also comes into being, so it helps in profit. But changing and slopping also, that will require new person in new they that will require more skilled persons and some new technologies, which the companies will not like, because that will also result in your losing money, okay. So the profit will get slashed, so that may also incur in losses, okay. So they are like a stable system, so that's why that is very important to be like, that is why the PET is there, because it is mature, because it has an established system. So that is a limitation. The results, one of the other limitation is results only raw consideration, okay. So there are many more factors which may be important are not considered. So data is limited on recycling process, okay. Avoided products not considered. Transportation biggest contributor to environmental impacts, and accurate data required for precise LCA. Okay, so due to uncertainties in LCI, there is life cycle inventory data. Results reported here are only for the raw consideration of the environmental impact of PLA and PET. Okay? So this is usually the uncertainties present in the LCI. The report here provided is for raw consideration of the environmental impact of PLA and PET. So the results might change with more authentic data. Okay. So one more case, let us see. That is microalgae to micro. One more case, how, like, based on microalgae to biofuel. Okay. So how, what is the LCA? What is the life cycle? Like, what is the life cycle emission, okay, or what is the, how does it perform in life cycle assessment when microalgae is used for biofuel, okay. So why it is important, generally microalgae, why it is being popular, because fossil fuel, it is non-renewable and it is in the verge of extinction. Crude oil and natural gas reserves will be diminished around 2051 to 52, that is after say 30, 25, 30 years. And coal might last a few longer, around 2100, that is about 75 more years or so. So biofuel, it is energy source made from living organisms or their metabolic byproducts. It can be prepared in much lesser time. The first generation, it results in like, basically they use fermentation of sugar, starch, or trans esterification process of vegetable oil. Example: ethanol, biodiesel, bioalcohols, green diesel, biofuel, gasoline, bioether, biogas, syngas, solid biofuels, etc. The second generation, they use lignocellulosic bio mass and such feedstock. Example is cellulosic ethanol, algae-based biofuels, biohydrogen, methanol, dimethyl furan, etc. The third generation, they use basically microalgae, okay, and they also help in carbon sequestration. So this is generally a process of life cycle. So firstly, the raw material comes from the source, raw material source. They are taken as materials, and the manufacturer goes in the industry. Then they are packed, that is packaging, transported, that is distribution, used by the consumers, and finally they go reuse, recycle, or disposal. Okay, so if they are reused and recycled, again they are taken as materials, and again they go for manufacturing. So this is a circular, like basically a circular economy, if it goes in a circle. So this is basically how the life cycle is carried, okay, goes. And if you remember this diagram, so that is a very standard basic diagram of life cycle assessment. So there are three steps which are interconnected with the fourth. So goal and scope definition, environmental goal and scope definition, inventory analysis, and impact assessment, all are connected with interpretation, okay. So these are the phases, in the most important phases of life cycle assessment, okay. So if you see here, the objectives for this, in the algal mass biomass plant, basically, that is from microalgae to biofuel, if you perform the LCA, here the objectives is firstly estimate the carbon footprint of the microalgae to biofuel manufacturing process using hydrothermal liquefaction or HTL. Secondly, to compare the potential impact between two conversion process, that is HTL or hydrothermal liquefaction and pyrolysis. Thirdly is the comparison of potential impact between biodiesel, bio-oil, and fossil fuel diesel. Okay, so these are the objectives for the LCA. So if you see here, based on these life cycles, if we assessment, if you see the stages, so the raw material and energy are coming here during raw material acquisition. So the manufacturing is going on. The energy is required during manufacturing. So based on this, we are using the product, and after that reuse and maintenance, and finally recycle and waste management. And based on this, the output is basically uh, the outputs are basically atmospheric emissions and co-products. Okay, so these are the outputs, and yeah, so these are the energy change which is happening. Okay, so there was a term in the previous classes, I forgot the term. So that basically represents the flow happening. Okay, the flows, yeah, it was elementary flow. So this is the elementary flow, the input elementary flow and the output elementary flow. Okay, so if you talk about the microalgae conversion pathways, so the microalgal biomass, so they have four pathway. One was basic pathway, one is biochemical conversion, one is thermochemical conversion, one is chemical reaction, and one is direct combustion. So biochemical conversion, it has further three pathways. One is photobiological hydrogen production that results in hydrogen. One is anaerobic digestion, which results in biogas. One is fermentation, which results in ethanol. In the case of thermochemical conversion pathway, so it has three further pathways. One is gasification that results in syngas or synthetic synthesis gas. One is pyrolysis that results in bio oil or syngas. One is liquefaction, which results in bio oil. In the pathway of chemical reaction, it results in transesterification that results in biodiesel. And for the case of for the pathway of direct combustion, that results in power generation, and that results in electricity. So if we describe the process description, microalgae to biooil through HTL, that is hydrothermal liquefaction. So these are basically the main 8 processes. CO2 mass transfer, then microalgae cultivation, harvesting, then cell separation, then hydrothermal liquefaction, then stabilization, then hydroprocessing, and at last biooil is produced. Okay. So the goal of the LCA study is to assess the potential environmental burden and impact of biooil production using power plant flue gas through HTL hydrothermal liquefaction process at an algal biomass plant in eastern India. Scope of the LCA study is a gate-to-gate system boundary. Mainly the manufacturing process and co-products are subjected to this study. The functional unit of the LCA study is 1 kg of processed biooil produced by the plant. Okay. The assumptions considered are growth of microalgae follow phototrophic, that is use of light pathway, using sunlight as the energy source. Algal biomass absorbs sunlight uniformly. Climatic conditions remain unaltered or unchanged during 20 days cycle of algae cultivation. Hydrothermal liquefaction HTL plant is co-located with algae production plant. Exclude those parts which have less than 0.5% impact overall. Construction and maintenance of plant do not have significant environmental impact, thus excluded from the LCIA study. Okay, so these are the assumptions. So if we talk about the this one, the HTL, and similarly if we talk about the microalgae to biooil through pyrolysis, okay. So the this one was for HTL, okay. So if you see compare this one with this one, you will see that removing the HTL process, there are two more processes added. Okay, the first four are the same up till cell separation, and the last year also same from stabilization to bio oil. Okay, so in between, in place of HTL, two more processes, drying and pyrolysis is added. Okay? So it is CO2 mass transfer, then microalgae cultivation, then harvesting, then cell separation, then drying, pyrolysis, stabilization, hydroprocessing, and bio oil. Okay. So this is an inventory comparison for pyrolysis and hydrothermal liquefaction cases, HTL cases. So these are the steps, units, pyrolysis, and HTL values. Okay. And similarly, based on the CIMA-PRO analysis, so impact assessment, so comparative life cycle impact assessment of bio oil HTL, bio oil pyrolysis, and biodiesel recipe midpoint H V1.10 world recipe H. So these are the values for the various impact categories and units with units. Okay. So for bio oil using HTL, bio oil using pyrolysis, and biodiesel. Okay, so these are the values. So the conclusion was comparative LCA study of bio-oil production through hydrothermal liquefaction and pyrolysis process. NER or net energy ratio for HTL process is 0.914, and for pyrolysis process it is 2.383. The global warming potential for HTL process is 10.225 kg CO2 equivalent. For pyrolysis it is 38.33 kg CO2 equivalent. For biodiesel 23 kg CO2 equivalent, and for fossil fuel diesel it is 311 kg CO2 equivalent. Okay, so from this we can say biodiesel is the best. Okay. And the comparing recipe impact assessment results, the best alternative is bio oil. Okay, through HTL process. Okay, with the lowest normalization score of 0.107. So the this is one of the observation that has been found total. And for future scopes, full-scale LCA including construction phase, transportation phase, and use phase can be done. Comparative study of different conversion pathways can be done. Comparative study of different feedstocks can be done. Use of produced bio oil as energy source to substitute power plant energy, so that can be also done. So these are some important topics on which the life cycle assessment can be done. So now let us go to some tutorials. Okay, so some lecture tutorials have been followed. So based on the previous classes, all the classes, because this week course is basically a summary. Okay, summary and case study. So case studies we have done. Now let us go to some problems. Okay, some tutorial problems based on the previous class topics. Okay, so one is the one topic is method detection limit, MDL. So if you remember, it is the minimum concentration of a substance that can be measured and reported with 99% confidence that the analyte concentration is greater than zero and is determined from analysis of a sample in a given matrix type containing the analyte as per EPA 1992. So MDL is T into S, and T is in terms of n minus 1, and alpha is 0.99, where Tn minus 1 alpha equal to 0.99 is one-sided critical T value at 99% confidence level, and n is the number of samples, and S is standard deviation, right? So let us see this problem, similar problem which we had done at during that class. So calculate the method detection limit with 99% confidence level for the following sample analysis results. Solution. So this is the basically these are the values. So based on that, we need to calculate the method detection limit. Okay. So these are the samples ranging from 1 to 8, and these are the results in milligram per liter. 12.11 milligram per liter, 12.02, 12.21, 12.06, 12.57, 12.42, 12.09, and 12.32. Okay. So the number of samples are 8. So the average of the sample data is 12.225 milligram per liter. The standard deviation has been found to be 0.19 milligram per liter, and sorry, it is unitless. It is 0.19, and for determination, we know that MDL is equal to T n minus 1 alpha equal to 0.99 into S. So n is 8. Okay, and standard deviation, it comes to be 0.19. Okay, so T n minus 1 alpha equal to 0.99, and that is T 8 minus 1 alpha equal to 0.99, that is T 7 alpha equal to 0.99. Okay, so that the value of T and n minus 1 equal to 7 and alpha equal to 0.99, it comes to be 2.998. So you can see it from this table basically. For this 7, so n minus 1 7 means 7 degrees of freedom. Okay, so 7 degrees of freedom, and for alpha equal to 0.01, sorry, alpha your alpha 0.99, so alpha minus 1 to be 0.01, so this value comes to be 2.998. Okay, so this is 2.998, so therefore the value of MDL is 2.998 into 0.19. Okay, so S T into S, so this comes to be 0.57 milligram per liter. Okay, so this is the answer. That means uh, for these results, okay, the method detection limit is 0.57 milligram per liter, and this means that 0.57 milligram per liter would be the minimum concentration that we can trust with 99% confidence level. Okay, so that is the meaning. And this is the this is a table. So here the TA value, Okay, so the table entry which shows the TA value. So TA is basically having an area to the right, okay, of A, right, of that A value under a T distribution. This is the T distribution with T DF, degrees of freedom. Okay? So more is the A value, lesser will be the TA value. Okay, so more is the A value, lesser is the TA value. Lesser is the A value, more is the TA value, because lesser will be the A value. Okay, so if A is here, say for example, if A is 0.025, it will be here. Okay, so if it is here, then the values will be higher. Okay, so like this, because the area will be more. Okay, so that is how it is basically calculated. Okay? So similarly, if you go even more less, so it will be more high. Okay, so if you more at a 0.01 means it will come here, 0.005 here. Okay, 0.0005 here. Okay, so more the area will be in the right side. Okay? So second topic. Okay, so let us go to the second topic is mass balance and control volume. Okay, so this is a powerful and useful tool for studying how chemicals behave in the environment. So it basically consists of input, control volume, and output. So input is the input which is influent, which is coming. Output is the effluent concentration, and control volume consists of sources, sinks, and reactions. Okay. So for any control volume, the change in storage of mass per unit time, it is equal to input minus output plus sources minus sinks. Okay. So many processes are analyzed at steady state. So at steady state, it means that the change in storage is zero. Okay, so with time it is not changing. Okay, and hence the concentration and mass in control do not change. Control volume do not change with time. It gives input plus sources. It is equal to output plus things. Okay, so that is the meaning. And so let us take an example. Let us take a problem for that. So half a bottle of ethanol was used for preparing the stock solution in chemistry laboratory. After completing the experiment, the students placed the chemical bottle uncorked. So they did not put the cap again, the cork again inside the bottle. Initially, the bottle contained 400 grams of ethanol. Okay, the unsealed bottle loses ethanol at a rate of 0.5 grams per day. After sitting in the cabinet over the summer 90 days with the cork removed, how much alcohol remains in the bottle? So that is the question. Okay, so what is the amount of alcohol that is remaining in the bottle after 90 days? Okay, yeah, after 90 days the bottle is left uncorked. Okay, so the solution is, let's see, so given data, amount of ethanol in bottle is 400 grams. Okay, amount of ethanol present after the experiment, because half of the bottle was used, okay, for preparing the stock solution. So half is remaining. Okay, so after experiment half is remaining, that is half of 400, that is 200 grams. And the loss, okay, rate of loss of ethanol is 0.5 grams per day. Okay, so because it was unsealed, so rate of loss of ethanol is 0.5 grams per day. Now therefore amount of ethanol evaporated after 90 days, it will be 0.5 into 90, right? So that comes to be 45 grams. And because 200 was there, okay, so removing 45 from 200, we get 155, right? So therefore amount of ethanol in the bottle after 90 days, it will be 155 grams. Okay, and that is a representative sketch for that. Okay, so the answer is 155 grams. One more mass balance numerical. So a printed circuit board manufacturing plant is discharging the chemical 111 trichloroethane TCA into a river that subsequently flows into a lake. The source of drinking water for a small town. The levels of TCA in this lake currently fail to meet drinking water objectives of 10 ppb, parts per billion. As an environmental specialist with the Central Pollution Control Board, you have been asked to help determine discharge requirements for the manufacturing plant by assuming that the lake is a well mixed system, that concentrations are at steady state, and that the only process acting on this chemical in the lake are volatilization and biodegradation. How high can the influent concentration of TCA seen be at the point where the river enters the lake? Okay, so we need to basically find the scene. Okay, that is the influent concentration of TCA, trichloroethane 111. So these are some of the data provided for the problem. So volatilization rate is 3 into 10 to the power minus 4 microgram per centimeter square second. Biodegradation rate is 6 into 10 to the power minus 3 micromolar per day. River inflow to lake is 758 liter per minute. River outflow from lake is 758 liter per minute. So inflow and outflow are same. Lake volume is 5.7 into 10 to the power 6 liter per minute, and average lake depth is 10 feet. Okay. So let us see how to solve the problem. So if we draw the flow chart, basically flow chart of the flow happening. So this is the control volume CV, this is the input, this is the output. So input, the inflow to lake is 758 liter per minute, and same is the output or outflow from lake. Okay. And the in control volume, basically we have volatilization rate sink, which is 3 into 10 to the power minus 4 microgram per centimeter square second, and one is biodegradation rate, which is also sink, which is 6 into 10 to the power minus 3 micromolar per day. And there are two sources which have two parameters which have no sources. One is the lake volume. Okay, it does not have any input, so it is 5.7 into 10 to the power 6 liter per minute, and other is surface area, which is 1867 square meter. So these are the informations we get from here basically. Okay, so here, and also I think, okay, these values have not been provided. Yeah, this is provided, but I think, yeah, so this is not provided surface area, so that is also, I think, a part of the problem. Okay, so now let us go to the solution. So if since it is steady, okay, so it is a steady state, so therefore if it is a steady state, the change in storage is 0. So therefore this is 0. Okay, and this will be equal to rate of mass in minus rate of mass out plus rate of mass source minus rate of mass sink. Okay, so as there are no sources provided, so this is 0. So that means mass in minus mass out minus mass sink equal to 0. And this mass sink is basically two. One is volatilization and one is biodegradation. Okay, and the drinking water objective for TC is 10 ppb. So as an output we need 10 ppb, okay, of this one drinking water objective. So in the outflow we need 10 ppb of this one trichloro uh, ethane, okay, 111. So this is the drinking water requirement. Okay, so uh, if you see here, so using that equation we find that mass inlet is equal to mass outlet plus mass sink. Okay, so now let us calculate this both of them. So mass out is equal to 758 liter per minute. Okay, that is out into, so if we convert this liter per minute into into milligram per minute, okay, in terms of the TCA, so we multiply by 10 microgram. So ppb equivalent in microgram per liter is 10. Okay, so 10 ppb is 10 microgram per liter, and 1 milligram is 10 cube microgram. Okay, so for cancelling this, so converting this in terms of TCA, we get this one 7.6 milligram per minute, and the rate of mass sink is addition of rate of volatilization mass plus biodegradation mass. Okay, so let us calculate both of them. So volatilization mass is 3 into 10 to the power minus 4 microgram per centimeter square second. So this value is given in the question. So multiplying by area, okay, that is 1867 meters square, and converting the units, and basically, yeah, so basically converting microgram per second to milligram per minute, we get it to be 336 milligram per minute. Okay, and similarly my biodegradation rate of mass of biodegradation, so it is 6 into 10 to the power minus 3 micromolar per day. So converting that into mole per minute. Okay, so will be needing the volume, okay, which is provided in the question. It is 5.7 into 10 to the power 6 liter, and 1 molar is 10 to the power 6 micromolar, and mole is mole per liter. Okay, so cancelling, and it is for 1 day, so we need to convert into minutes. So 1 day is 1440 minutes. So converting the units and multiplying by volume, we get the rate of mass biodegradation as 2.4 into 10 to the power minus 5 mole per minute. Okay, so molecular weight of TCA, that is C2H3Cl3, it is 2 into 12. 12 is the unit mass of molar mass of carbon. One is hydrogen, and chlorine is 35.45. So the molecular weight of TCA, that is 111 trichloroethane C2H3Cl3, it is 2 into 12 plus 3 into 1 plus 3 into 35.45, which is approximately equal to 133 gram per mole. So the rate of mass biodegradation, it is equal to 133 gram per mole. Okay, and multiplying because this, yeah, so this we have calculated because we need to convert this. Okay, so this is the unit basically. Milligram per minute we have to convert. Okay, so this is in mole per minute. So milligram per minute, so gram is there, minute is there, so we need to convert this mole. Okay, so for mole we'll be multiplying this with the molecular weight. Okay, so multiplying 133.4 into 10 to the power minus 5 and converting the units, we get the rate of mass bio degradation as 3.2 milligram per minute. Okay, so therefore the rate of mass sink is 336 plus 3.2, which is 339.2 milligram per minute, and therefore the rate of mass in will be this sink plus out. Okay, so sink is 339.2 and out is 7.6, right? Everything is in terms of TCA. Okay, and therefore the rate of mass in is 346.8 milligram per minute, and uh, therefore, per river inflow rate is 346.8 milligram per minute. Okay, and the inflow of concentration of inflow, rate of inflow is 750 liter per minute. So multiplying that, we get basically the value in milligram per liter. Okay, so which can be converted in ppb. So that is 0.46 milligram per liter, or say influent concentration of TCA is 460 ppb. Okay, so that is required if we want to have a effluent TCA concentration of 10 ppb. Okay, so if we have more than this, it can be it will not be possible to have 10 ppb of the TCA, which is the drinking water level. Okay, so let us go to some other topics. So the initial, this is one of the initial most topic of this course, that was IPET equation. Okay, so IPET equation is used to assess the magnitude of sustainability challenges. So the equation is basically I equal to P into A into T, where I is the impact, P is the population, A is the affluence in terms of gross domestic product (GDP) of a nation or region, or number divided by the number of people in the nation or region. Okay, and T is the technology used for delivering GDP. Okay, so let us try a problem using the IPET equation. Find the estimate the percentage increase in the amount of energy that would be required worldwide in 2060 relative to 2010 to estimate the increase in population and affluence. Assume that population grows 1% per year, global economic activity per person grows 2% per year, and energy consumption per dollar of GDP grows 1% per year. How much does this estimate change if population growth is 2%, economic growth is 3%, and energy consumption per dollar of GDP growth is 2%? Okay, so if it is 1%, 2%, 1%, how does it differ from uh, how does it change when it is 2%, 3%, and 2%? Okay, so let us see that. So this is the equation: I equal to P into A into T, where P is population, A is affluence, that is GDP by number of people in that region, and T is technology. Okay, so yeah, so let us for trivial sense, okay, because the values are not given, let us take the population, affluence, and technology at a particular at the initial population, affluence, and technology is 1. Okay, let us consider as 1, and then it has been mentioned that it in the first case it has been mentioned that population grows 1% per year, economic activity or affluence grows by 2% per year, and energy consumption or technology grows by 1% per year. Okay, so that has been given, and number of years is 2060 minus 2010. Okay, so in 2010 let us take it as 1. Okay, so number initial year. Okay, and number of years to be considered is 50 years, right? So therefore taking 1%, 2%, and 1%, so the I, that is the impact, will be 1 plus 1 by 100 whole to the power 50 into 1 plus 2 by 100 whole to the power 50 into 1 plus 1 by 100 to whole to the power 50. So impact will be 7.28%. Okay, similarly if we change the P value with 2%, A value with 3%, and T value with 2%, okay, so that value I2 will be 31.76%. Okay, so the question is how much does this estimate change? Okay, so the change will be 31.76 minus 7.28. Okay, so it has been shown here, so therefore percent increases 31.76 minus 7.28%, that is 24.48%. Okay, so that is the answer. One more question. Second numerical: each year approximately 10,000 persons lose their lives in vehicular accidents in a state of population 100 million. How many fatalities would be expected over a 2-day weekend in a city of that state having population 5 million? Okay, so we need to find if 10,000 persons lose lives in a state, okay, in a state which is having population of 100 million, how many fatalities would be expected over a 2-day weekend, okay, in a city of state having 5 million population, okay. So the date is 10,000, okay. So that is for 1 year, okay. 1 year 10,000 persons lose lives in 100 million population. So how many will lose in 2 days, okay, in a city of 5 million, okay. So here date is 10,000 percent, so that is the risk, okay. And risk is equal to population into exposure into hazard, okay. So exposure is calculated in terms of year. So in the given in the first case, like in the given information, it has been given that each year, that is year is one, okay, one year exposure time is 1 year, population is 100 million, and risk is 10,000, okay. So from that we can calculate the hazard, okay, that is equal to 10,000 by population, that is 100 into 10 to the power 6 into exposure time, which is 1, okay. So we get the hazard is 10 to the power minus 4 death per people per year, okay. So therefore we need to calculate the fatalities, that is risk, okay. So we have the population is 5 into 10 to the power 6, exposure time is 2 day, that is if you convert into year it will be 2 by 365, and hazard is this one 10 to the power minus 4, okay. So it will be hazard will be same because we are considering a city of that particular state itself, okay? Of that state itself, so it will be same hazard. So it will be 10 to the power minus 4, therefore multiplying the three population, exposure time, and hazard, we get the risk as 2.74 deaths, okay. So this is the answer. Third numerical, assume that a 5 watt fluorescent bulb provides the same illumination as a 25 watt incandescent bulb. Calculate the mass of coal that would be required to generate the additional electricity required for an incandescent bulb than a fluorescent bulb for 100 hour life. Assume assume that assume transmission losses of 15% and electricity generation of with 40% efficiency and 8 kilowatt hour per kg for the heat of combustion of coal, okay. So we basically need to find the mass of coal that would be required to generate the additional electricity uh, if incandescent bulb is used instead of fluorescent bulb for 1000 hour life, okay. So the solution is starts like this. So fluorescent bulb it gives 5 watt, okay. Incandescent bulb it so 5 watt fluorescent bulb provides same illumination as 25 watt, okay. So therefore if we want to have incandescent bulb, okay, so we will need 20 watts. So we'll need to have so incandescent bulb it is 525 watts, okay, and fluorescent bulb is 5 watts. So additional requirement if you use incandescent bulb, so sorry, if you use fluorescent bulb, the additional requirements will be 25 minus 5, that is 20 watt, right. So additional electricity requirement it will be taking 1000 hour life, it will be 20 to 1000 by 1000, that is 20 kilowatt hour. And additional electricity requirements considering transmission losses of this one 15% and electricity generation of 40%, okay. uh, so if we talk about this, so it will be so for this generating this 20 kilowatt hour we will be needing 58.82 kilowatt hour of additional electricity, okay. So therefore the amount of coal requirement it is 58.82 kilowatt hour divided by 8 kilowatt hour per kg, okay. So that is the heat of combustion of coal, okay. So basically it will be equal to 7.35 kg, okay. So dividing 58.82 divided by 8 we get 7.35 kg, okay. So that is the amount of 7.35 kg is the amount of coal that would be required to generate the additional electricity, okay. So next question, approximately 1 billion tons of coal is burned annually in the United States, providing 50% of the country's electricity consumption. The coal may either be moved by train from the mine to power plants near where the power is used, or the coal could be combusted near the mine mouth to generate electricity, and the electricity could be transmitted over long distances to the users. As a case study of this trade-off, consider electricity used in Dallas, which is generated in part using coal from the Powder River Basin (PRB) in Wyoming. Power. This is a place in US. It's a US state. Power plants using PRB coal supply 3 billion kilowatt hours of power per year to the Dallas area at an average conversion efficiency energy in the generated electricity per energy in the fuel burn of 19%. The coal mined at the PRB has a heat content of 7500 BTU per pound coal. 1 kilowatt hour is equal to 3412 British thermal units. Determine the amount of coal required from the PRB to support consumers in Dallas. If the energy required to transport coal by train is 0.003 gallons per ton mile, and the distance from the PRB to Dallas is 100 miles, what fraction of the total energy consumption is due to transport? Assume that diesel fuel has an energy content of 1,24,000 British thermal units per gallon. So this is a big question. So we need to find the amount of coal required. Okay, we need to find the distance. Sorry, we need to find the fraction of total energy consumption due to transport. Okay, so these are some of the questions. So let us see how to proceed. So the requirement of electricity in Dallas is 3 billion kilowatt hour per year. So it is provided somewhere. This one, 3 billion kilowatt hour per year. The amount of coal required is therefore 3 billion, converting in terms of billion pounds. Okay, and dividing by the efficiency. So these values are provided in the question itself. So we can find there to be amount of coal required per year to be 7.18 billion pound or 3.25 million tons, because 1 pound is 0.453592 kg and 1 ton is 1000 kg. Okay. So therefore energy required for transporting coal is 3.25 million tons into this value, 0.003 gallons per ton mile. Okay, and mile is 100 miles into 100, and converting the units into billion BTU, so we'll again multiply by 1,24,000 BTU per gallon, this value. So we get the value as energy as 120.9 billion BTU, British thermal units. So therefore the energy consumption, it is equal to 3 billion kilowatt hour into 3412 BTU per kilowatt hour divided by 0.19. So that is basically 3 billion is the this value, and that is into 34112 BTU per kilowatt hour. So that is the value, this one. Okay, and basically we are converting into British thermal units for 1 year, and because 19% is the efficiency, so we are dividing by 0.19. So the value is coming as 53,873.6 billion BTU. Therefore percentage energy requirement for transportation, it is 120.9 billion. So this is 120.9 billion BTU divided by the total 120.9 plus 53,873.6 and into 100, because we need in percentage, so we get the value as 0.22%. So that is the answer basically. Okay, so the question seems to be very large, but if you see the if you know like what to actually find, it is not that large. Okay, so the answer is 0.22%. Okay, so we with this we come to the end of the lecture. Okay, the 8-week lecture. So now let us go for problem solving by taking some handful of standard problems. So let us start. So which of the first question, which of the following is not among the steps as part of performing life cycle impact assessment? A, classification; B, characterization; C, cascading; or D, evaluation. A, B, C, and D. So if you see here, the classification is there in life cycle impact assessment, characterization is also there, evaluation is also there. What is not there? It is cascading. Okay, C. So C, cascading is the right option. So C, cascading. So it is basically refers to flow, fall, or hanging down of large quantities like waterfall. Okay, so that is not a step in performing life cycle impact assessment. Second question, environmental indicators such as GWP, that is global warming potential; ODP, that is ozone depletion potential; ARP, that is acid rain potential; and SFP, that is smoke formation potential, are based on cause and effect mechanisms involving what? A, electronic and electrical properties of pollutants; B, physical and chemical transformation of pollutants; C, optical and magnetic properties of pollutants; or D, none of the above. So which is the correct option? A, B, C, or D? So these indicators are cause and effect mechanisms involving electronic, not electronic and electrical properties. So this is not correct. Physical chemical transfer, yeah, this is correct. Optical magnetic, this is also not correct, and none of the, so this is correct, so this is also not correct. So B, physical and chemical transformation of pollutants is the correct option. Okay, so if you see B, physical and chemical transformation of pollutants. Third question, calculate the percentage of the overall impact of global warming potential for the dinitrogen oxide. This is for the this value, for this basically nitrogen oxide for the given emission data. So this is the data provided. So what is the percentage? Okay, so is it 12.8, is it 1.56, is it 1.28, or is it 0.34? Okay, so let us see. So the percentage basically, it is basically, it will be product of this divided by summation of all the products. Okay, so this is equal to 0.35 into 298 divided by 0.35 into 298 plus 6570 into 1 plus 15 into 100. Okay, and the value is multiplied by 100 to convert into percentage. So by performing that, you will get the value as 1.28%. So C, 1.28% is the correct option. So C, 1.28 is the correct 1.28% is the correct option. Fourth question, calculate the acid rain potential ARP in gram for the coal, oil, and natural gas in respective order with the emission data presented in table for 1 kilowatt hour electricity. The acidification potential for nitrogen oxides is 1.07 and sulfur dioxide is 1.0. So since only nitrogen oxides and sulfur dioxide is provided, the others will be considered as zero. Okay, the acidification potential. So we'll only consider these two. Okay, and so therefore for this one for hard coal, soft coal basically, so it will be 1.07 into 2.55 plus 1.0 into 5.27, like this. So as you can see here, so the value is 8, so it is this A. Okay, similarly for oil, it is 1.07 into 2.75. Okay, and 1.0 into 6.60, so it is 9.54. Okay, and for natural gas, it is 1.07 into 0.37 plus 1.0 into 5.79, this is 6.19. Okay, so A, 8, 9.54, 6.19 is the correct option. So as you can see, A, 8, 9.54, 6.19 is the correct option. Fifth question, calculate the smoke formation index in gram for the given emission data. The smoke formation potential for NMVOC is 3.10 and sulfur dioxide is 0.015. So what is the smoke formation index in grams? Is it A, 391 gram, B, 0.391 gram, C, 444 gram, or D, 0.444 gram? Okay, so here also, only because NMVOC and sulfur dioxide is given, so we'll consider others as potential value as 0. Okay, so therefore for this data, the smoke formation index will be 3.10 into 0.12614. So we are converting, because we need in gram, we'll convert milligram. So it will be 3.10 into 0.12614 plus 0.015 into 3.56. Okay, so the value will come to be 0.444 gram, that is D. Okay, so D, 0.444 gram is the correct option. So as you can see, D, 0.444 gram is the correct option. Sixth question, which of the following is not a social performance indicator? A, poverty, B, demographics, C, governance, D, climate. So out of A, B, C, and D, which is correct? So poverty is a social performance indicator, demographics is also a social performance indicator, governance is also a social performance indicator. Climate is not related to social indicators. Okay, so it is not related to society. So D, climate is not a social performance indicator, so D, climate is the correct option. Basically the options are self-explanatory. Okay? So D, climate is the correct option. Okay, seventh question, the relative importance of each environmental impact category is assessed so that a single index for environmental performance can be developed. This activity is performed in which step? A, classification, B, characterization, C, cascading, or D, valuation. A, B, C, and D, out of this, which is correct? So this if you remember, so this development of this single index for environmental performance, it is done in impact assessment category, impact category in the third step. Okay, impact assessment category in the third step, which is the valuation. Okay, so first is classification, second is characterization, third is valuation. So D, valuation is the correct option. So D, valuation is the correct option. Eighth question. The results and values of GWP, global warming potential, ARP, acid rain potential, SFP, smoke formation potential, for different sources of electricity will lead to A. Informed decisions about investments in future power production, B. Consumer decision making on whether or not to purchase green power, C. Increase the cost of conventional energy, or D. Decrease the cost of green power. So which of these are correct? Okay. So these values for different sources of electricity will lead to what? So informed decisions about investments in future power production. So that is correct. A is correct. B, consumer decision making on whether or not to purchase green power. So this is also correct. So for this you can refer to the initial slides. Okay, so we talked about this. C, increase the cost of conventional energy. So that is not correct. It will reduce basically. And D, decrease the cost of green power. Okay, so that is also not sure. Okay, so it may like based uh, based on this. Okay, so it may also increase the cost of green power. Okay, so for that also we need to have to perform LCA. So that is also not correct. That is why the consumer decision making on whether or not to purchase green power, it will lead. Okay, so it is not like certainty that green power will mean your cost is less. Okay, it may be high also. Okay? So therefore A and B are the correct options. So as you can see, A, informed decisions about investments in future power production, and B, consumer decision making on whether or not to purchase green power. So both are the correct options. Ninth question, which of the following is or are the endpoint damage indicators in the emission of CFCs, chlorofluorocarbons? A, is it ozone layer depletion? B, marine life damage? C, skin cancer? D, ozone loss to stratosphere? So out of A, B, C, and D, which is the correct option? So if you remember the first or second slide, okay, so this was the flow chart. So there is for emission of CFC. So if you see here, the ozone layer depletion, so that is basically a midpoint damage indicator. Sorry, this one. Ozone layer depletion midpoint damage indicator. So that is not an endpoint. Okay, marine life damage, yeah, so that is an endpoint. Okay, skin cancer, skin cancer is also endpoint. Okay, and ozone loss to stratosphere, ozone loss, so it is also midpoint, not endpoint, so that is not correct. Okay, B and C are the correct options: marine life damage and skin cancer. B and C. So as you can see, B, marine life damage, and C, skin cancer, so both are correct. Okay. So last question. So 10. Which of the following statements are correct? A. Environmental indicators are based on physical and chemical transformation of chemicals. B. Indicators of human health rely solely on subjective factors. C. Multi-pathway exposure of contaminant to human includes ingestion, inhalation, and dermal route. Or D. Tracy TRACI method uses science-based indicator for human health impact assessment. So out of A, B, C, and D, which are the correct options? Okay. So A, environmental indicators are based on physical and chemical transformation of chemicals. So it is true. So environmental indicators are certainly based on physical and chemical transformation of chemicals. So A is correct. B, indicators of human health rely solely on subjective factors. So this is wrong. This is not correct. So if you remember, the indicators of human health rely both on objective as well as subjective factors. So objective is physical and chemical. Okay. So this is incorrect. Okay, B is not correct. C, multi-pathway exposure of contaminant to human includes ingestion, inhalation, and dermal route. So this is correct. Multi-pathway exposure of human-related contaminant. It can include ingestion. It can be through nose, inhalation, and it can be through skin, dermal. Okay. So C is correct. And D, PRESI method uses science-based indicator for human health impact assessment. So that is also correct. This method uses science-based indicator for the human health impact assessment. Okay. So A, C, and D are the correct options. So as you can see, A, environmental indicators are based on physical and chemical transformation of chemicals. C, multi-pathway exposure of contaminant to human includes ingestion, inhalation, and dermal route. And D, Tracy method uses science-based indicator for human health impact assessment. So A, C, and D are the correct options. Okay. So with this, we come to the end of this course. Okay, so I hope that you have learned something out of it, and you can apply it in your future endeavors. So let us, with the hope that we will meet in a new NPTEL course next semester. So let us end this course. Okay, so I wish you all the best for the exams, and hope that you succeed in your life. Okay, thank you. Bye.